So in this second class of interference, first you have to study what are coherent sources. See, without reading the first class of interference, don't look at this class 2. See, what are coherent sources? See, two sources of light emitting waves. They should emit under the condition that first one is same frequency. So light wave should have same frequency. Then same amplitude. Their amplitude should be same. And either they are in phase or they should maintain a constant phase difference. If the two sources of light satisfy these three conditions, then they are said to be coherent sources. So waves must have same amplitude, same frequency. Either they are in phase or they should maintain a constant phase difference. What is this? I hope you know what is same frequency and same amplitude. See here, phase is 90 degree, here phase is 90 degree, phase difference is 0. And similarly here it is 180 and here also 180. Phase difference is 180. At every point, the phase difference is 0. The two waves are said to be in phase. Or they should maintain a constant phase difference. They should maintain a constant phase difference means, see here, this is one wave traveling in the medium, and this is another wave also traveling in the medium. The phase difference between them is 2 pi. Means here to here 2 pi and here to here it is 4 pi. And here to here it is 2 pi. And difference is 4 pi minus 2 pi. It is 2 pi. Throughout in the medium, they should maintain a constant phase difference. If the two sources of light satisfy under these conditions, then they are said to be coherent sources. Now, two independent sources cannot become coherent sources. Two independent sources cannot become separate sources. This is one source and another source. They never be a coherent. Then why? See, if you supply heat energy either by electric discharge or some by means, atom goes to the excited state and there it remains and comes to the ground state emitting the light. How the light is formed? Always atoms are excited due to heat or electric discharge. While coming to the ground state, they emit the light. Each bulb contain or each source of light contain billions of atoms. At different instance, they goes to the excited level and comes to the ground level. Then how coherent sources are produced? If you consider here it is a single source of light, and in front of this light I put a screen having a narrow slit. Narrow slit. You know, the light spreads in all directions. Here also it enters, here also it enters. See, I am observing from this end. I cannot see that bulb, but I can see the light coming from two narrow paths. And if I write one is S1 and another one is S2, I can say that the two sources of light, S1 and S2, they are coherent sources. Because they are coming from the same source, they satisfy all three conditions. So same frequency, same amplitude, and they maintain a constant phase difference, or maybe phase difference between them is zero, because I have used a single source. From the single source it is divided into two. After passing through the two slits or two narrow holes on the screen, the lights are said to be coherent. So remember that two independent sources of light cannot act as the coherent sources. To produce the coherent sources, you should split the light coming from the single source. Then in the last class I studied that alternatively bright, dark, again bright, again dark bands are observed on the screen due to interference. And what are the conditions we should get a constant or sustained interference? The first condition is the two sources of light should be coherent. Means under what conditions we can get a good fringes. Alternately bright dark bands are called as fringes. Under what conditions? First, they should be coherent. Then second, same frequency. And third one is same amplitude. The two sources of light must be coherent, same frequency, same amplitude. And fourth one is the two sources of light should be very, very narrow. So assume that this is your screen and there are two paths. One is S1. Say this is S1 and another one is S2. These two sources of light should be very, very narrow, small. Then fifth condition, they must be very close. That means they should not be at large distance. The two sources of light should be very, very near. Then, sixth one, the screen must be placed at a large distance from the coherent sources. Then, seventh one, the two interfering waves, this wave and this wave, they must be under same state of polarization. That means either the light should vibrate, both the light should vibrate in the same direction. So vibrations are parallel to the board. This is due to S2 and this is S1. Or both should vibrate in this direction. The two lights should be in the same state of polarization. If these conditions are satisfied, you are going to get a sustained interference, very nice interference. Then these are the conditions for the sustained interference. So, what are the different methods to produce coherent source? So, by what means we can produce the coherent source? Two sources. First one is division of wavefront. I have explained in the last class very clearly what is wavefront. A division of wavefront means, see, this is the source of light. This is one wavefront, and this is another wavefront. This is third wavefront. Like that, wavefront travels in the medium. Then, in their path, if you put two narrow slits, then this wavefront advances when it falls, and through one slit the wavefront travels, through another slit also the wavefront travels. This is one wavefront and this is another wavefront. Earlier there was a single wavefront. After passing through the two slits, we have divided single wavefront into two. So this is coherent sources and this is another coherent sources. Then second, division of amplitude. That means we have to divide amplitude. Is it same as the division of intensity? Yes. Why? You know that this I is directly proportional to A square. If you divide this amplitude, intensity also divided. Then consider in the case of reflection of light and refraction of light. Reflection, refraction and transmission. How this intensity is divided? See, Consider this is one denser medium. If light of certain intensity from the source falls on the surface of this is air medium, this is glass medium. You know that at this point, the part of the light is sent back to the first medium. You are calling this as reflection of light. And the rest enters the second medium. By changing that angle, it is called as a refraction. Then here, part of the light sent back and it emerges in this direction. Then here it goes in this direction. See here, observe the light P and Q. Is that P and Q are the coherent sources? Assume that you are not observing this one, just like you are looking this through these 2 points. So light is coming from P and also from Q. These two are coherent sources. See, original intensity has divided into 2. In other words, amplitude is divided into 2. So this is another method of producing the what we have coherent sources. This is coherent source and this is coherent source. Then the same thing happens here also. It continues, this process, phenomena continues here. Multiple reflection takes place like this and it goes. Part of the light goes like this. These are the transmitted lights. Again, intensity is divided, decreased, because original intensity is here. If light takes multiple reflection, intensity goes on decreasing. So this is the phenomena which you are getting, that coherent sources, either by division of amplitude and another one is division of wavefront. There are 2 methods by which you can produce the coherent sources. One is division of wavefront, another one is division of amplitude. Next, we have to think of a device which produces coherent source. An optical device which produces a coherent source by the method of refraction is called as Fresnel biprism. You know that a prism produces a spectrum. Prism is one optical device. In the same manner, Fresnel is the name of the scientist. He is biprism. As the name itself indicates, there are 2 thin prisms . 2 thin prisms, this is one and this is another one. They are grounded and cemented together such that the 2 angles are acute angles. They are 30 minutes and another one is obtuse. It is 179 degree. So this Fresnel biprism produces coherent sources. Let us see how this biprism produces coherent sources. Now, experimental arrangement and the theory of biprism, we will ask this as a 10-mark question. First, let us see how this Fresnel biprism produces coherent sources. See here, P is the Fresnel biprism S is a monochromatic source placed at a distance A from this biprism, and light falls on this upper half and also this lower half, and it is deviated, refracted, and travels along this direction. If a person is observing from point B where the light is coming, he finds that the light is coming from one virtual point S1. And if you observe the C, this also appears to come from S2. So S1 and S2 are two coherent sources. So they are virtual coherent sources. So here this is the screen placed at a certain distance D. A is the distance of biprism from S. B is the distance of biprism from the screen. And the rays between AS2, the rays between this AS2, AS2 C, AS2 C, and another one is BS1E. They superpose, producing interference here. Within the cone AS2C and BS1E, so these two beams overlap and producing interference fringes on the screen. Now, so at this point the bright band is observed, is bright fringe, next followed by dark, bright, dark, like this. Alternatively bright, dark bands are formed on the screen. This is regarding your experimental arrangement. Now, theory. See here, S1 and S2 are two coherent sources in the biprism experiment. Then screen is placed at a certain distance D from these two coherent sources. So O is the center point. So consider one point P on the screen. So whether that point P is bright point or dark point, or at point P the fringe is bright or dark. Now we don't know, we cannot see it, it is only on the figure. See somewhere, so you are writing at this point it is P. Now follow this carefully. P may be bright or P may be dark. It depends on path difference between the two waves reaching that point P. What are those two waves? See, wave travels from S1 reaches the point P. Wave travels from S2, that also reaches the point P. Whether the two waves while reaching the point P have traveled the same distance or different distance, definitely they have traveled the different distance. S2P has traveled a longer distance than S1P, and there is a path difference between the two rays. This path difference between the two waves reaching that point, which one is longer? S2P minus S1P. You draw from S1 perpendicular to S2P, it cuts at K. Now extra distance is S2K. You observe from this S1 and K, these two, S1P is same as KP, but extra distance traveled by this wave is S2K. Therefore, this path difference is S2K. Then, see here, this angle is theta, this angle is theta, this angle is also theta. Therefore, this angle is also theta. So, what is this S2K? If you take the ratio of S2K divided by D, what is this D? D is S1, S2. Then S2K, this is opposite side divided by hypotenuse side, it is sin theta. Or this is your path difference S2K is D into sin theta, or this equation I want. This S2K, we got that D sin theta. What is that D? D is the distance between coherent source. If this theta is, P is close to O, bring this P is very close to O, theta is very small. If your theta is very, very small, then according to your trigonometric relation, I can write that theta is approximately equal to tan theta. If theta is very small, sin theta is approximately tan theta. Therefore, your path difference is equal to S2K, that is equal to, instead of D sin theta, it is D tan theta. Now with this tan theta, from this PQO, PQO, PQO. So this is angle theta. Tan theta is x divided by this d, or this is PO divided by QO. This is your PO divided by QO. What is PO? PO is the distance x of that point P from the center of the fringe system, and this is D. Therefore, this is x upon D. This becomes your tan theta. Therefore, tan theta is x by D. Substitute this in equation 2. So we have this path difference path difference is equal to x d divided by d. Call this equation as 3. So we are at the expression for path difference. So x is what? Distance of the fringe at point P from the center. Then d is the distance between coherent sources. Capital D is distance between coherent sources and the screen. Then whether that point P is bright point or dark point. I cannot say it, but I know the conditions. When that point P is bright point or constructive interference takes place, when that point P is dark point or destructive interference takes place. Let us see first constructive interference. That means first I will assume that point P is bright point. For constructive interference, we know that this path difference is equal to n lambda, which you have studied in the first class. If your path difference is n lambda, I will write that equation is n lambda is equal to x n d upon d. So why I have written this xn? See, this is bright center point, first point, second, third, fourth. So here nth bright band, 1, 2, 3, 4, 5, 6 like that of nth bright band is at point P. So from this your xn is equal to n lambda d upon d. Call this equation as 5. Then what is its previous band? Here this is xn. Its previous bright band, its previous bright band is xn minus 1. Therefore, for xn minus 1, I can write this as your xn minus 1 is equal to n minus 1 lambda d upon d. Call this equation as 6. Then what is the width of this band? So width of the band is defined as the distance between successive bright band gives the width of the dark band, or the distance between successive dark band gives the width of the bright band. Now we have assumed that point P is bright, then distance between successive bright band is represented by beta into d. D means what? Dark band. It is xn minus xn minus 1. This minus this. That means beta d is equal to, if you substitute here, n lambda d upon d minus this one, n minus 1 lambda d divided by d. Then this fringe width beta, it becomes, if you simplify this, you are going to get this is n lambda d upon d minus n lambda d upon d. That means n, it is lambda d upon d. You are going to get this equation. So, or if you simplify here, n lambda d upon d minus n lambda d upon d plus lambda d upon d. This cancels. So you are getting this B D, dark band. So this is the expression for the width of dark band. And how to find out the width of bright band? Assume that this point P is dark. If point P is dark, your path difference changes. Path difference is 2n plus 1 lambda by 2. Now path difference is 2n plus 1 lambda by 2. Here if you substitute, it is 2n plus 1 lambda by 2, that is equal to here xn d upon d. Then in the same manner, find out what is xn, then next xn minus 1, then subtract them. You are going to get the fringe width of the bright band beta is also lambda d upon d. Call this equation as 8. You observe that you work it at home. You observe that equation 7 and 8, the two equations are same. That means width of the bright band is same as width of the dark band.